Welcome to iTTV for Form 4 Physics. The title of this lesson, Measurement, Sensitivity of Measuring Instruments. In this lesson, we want to have a look at measuring. When we talk about measuring, there are a few key words that we need to understand. And this is what you need to be able to understand before the end of the lesson. You need to understand words like accuracy, which is close to the truest value. Consistency, which is being able to reproduce a value over and over again. We have errors, systematic error or random error. And also we have parallax error. All of these key words are the normal questions that you face in examinations. So by the end of the lesson, hopefully you will understand what they all mean. Measurements. In scientific experiments, we need to measure physical quantities. For example, a meter ruler is used to measure the length of a table in the laboratory. We can read the meter ruler to the nearest millimeter or even 0.5 millimeter, which is quite accurate enough. If we measure the thickness of a piece of paper, which is far less than 1 millimeter, we cannot use a ruler. We have to choose a more appropriate and precise measuring instrument, such as a pair of vernier calipers or a micrometer screw gauge. So try to understand what we are saying here. This is talking about sensitivity of measurement. If I wanted to measure the length of this table in this studio, I could use a ruler. A ruler has a centimeter scale on it. Now, the centimeter scale on this ruler will give me a measurement accurate to within 1 millimeter, or we would say 0.1 centimeters. But if I wanted to measure something thinner than that, like for instance, a piece of paper and how thick it was, well, I wouldn't be able to use a ruler for that. I would need an instrument that was more sensitive, meaning that it is smallest scale is better. I could use vernier calipers. A vernier caliper is accurate to 0.01 of a centimeter, which is much more sensitive than a ruler. For even more accuracy, I could use a micrometer screw gauge. Now, a micrometer screw gauge, as you can see down here, is accurate to within 0.01 of a millimeter. So, the smaller your finest division is, the more sensitive the instrument is. The ruler is 0.1 centimeter. The vernier caliper is 0.01 centimeter. And the micrometer screw gauge is 0.01 millimeter. Let's write these values down on the board so that you can understand what we mean by sensitivity. So, as we said, the ruler only measures to within 0.1 centimeter. So let's put that up here. The ruler, 0.1 centimeter. That's its maximum sensitivity. The vernier caliper has got a sensitivity of 0.01. So the vernier caliper is much more sensitive than a ruler. The micrometer screw gauge, so let's put this one in. The micrometer, its sensitivity is 0.01 millimeter. So if we compare all of these, it's clear to see that the micrometer screw gauge is the most sensitive because it can take a reading to the smallest amount, whereas the ruler is the least sensitive because its smallest reading is only 0.1 of a centimeter. So when we talk about sensitivity, we're talking about the smallest possible division that the instrument can take for us. Uncertainty in taking measurement. Whenever measurements are taken, some degree of uncertainty will be involved. The smallest scale division on the ruler is 1 millimeter. The uncertainty in reading the scale on the ruler is 0.1 centimeter plus or minus. Now in the slide, you've got a line. We've measured the line using a ruler, and the line is measured at 4 centimeters long. So let's go up to the board again and have a look at the problems we have with regards to uncertainty. So we have a line. Measuring with the ruler, we say that this line is 4 centimeters long. Now, the uncertainty of measuring with the ruler is 0.1 centimeters. This means that when I put the ruler down, here where the ruler measures 0, and here the ruler measures 4 centimeters. The uncertainty will occur at both points. At this end, we have an uncertainty of 0.1 centimeters. Over on this side, we have another uncertainty, again 0.1 centimeters. So when we measure a length like this of 4 centimeters, understand that our uncertainty occurs at both the beginning and at the end. So the uncertainty in this measurement would be 0.1 times 2, or you can just add the 2 up to give me an uncertainty of 0.2 centimeters. Which means this line, 4 centimeter, is plus or minus 0.2 centimeter uncertainty. That means there's this uncertainty that I have within a 0.2 centimeter value of its actual length. Sensitivity of instrument. The sensitivity is the smallest measurement that can be read. Consistency. How reproducible the result of the experiment is. The consistency of an experiment is a measure of the reliability of the experiment, or how reproducible the result of an experiment is. A consistent result may not be accurate result due to the fault of the measuring equipment, such as zero error of a micrometer. Accuracy. How closely the experimental results agree with a true or accepted value. The difference between accuracy and consistency. So on the screen, you will see that we've got 3 dartboards, A, B and C. Each give us a different set of values. So let's go up to the board and have a look at what we mean by consistency and accuracy using this board here. Now, if I have a set of values that are all very close to each other, like this, I can say that these values are consistent, but they are not accurate because the true value that I want is somewhere here in the middle. So this is consistent, but not accurate. If I have a system or a set of values that are all very close to the center like this, this is consistent and accurate because all the values are reproducible, they're close to each other, and they're all very close to the true value that I'm looking for. But if I had values that were spread around like this, well, these are A, not consistent because they're not anywhere near each other, and B, they're not accurate because they're not near the true value. So we can have, firstly, consistent but not accurate. We can have not consistent, not accurate, and finally, we can have consistent and accurate. Random and systematic errors. Random errors are caused by the uncertainty of the measuring instrument or slight changes in the quantity being measured. Random errors produce values which are scattered around the actual value, and their effect can be reduced simply by taking the average of a large number of measurements. Systematic errors are caused by a fault in the experimental arrangement or measuring instruments. Systematic errors generally produce values which are all above or all below the actual value and can only be corrected by fixing the fault in the experiment or instrument. If we look at the dartboard, you will see an example of random error. Our values are all scattered around. So, let's have a look at a random error here on the dartboard. When we have a problem that is causing a random error, we get values spread out all over, like so. The way to overcome a problem with a random error is we take as large a number of values as possible and then take its average. This will negate or reduce the random error in the experiment. So remember, with a random error, take as many values as possible and then find an average for it. Systematic errors come from the measuring instruments. Two types of systematic errors can occur with instruments having a linear response. Offset or zero setting error, in which the instrument does not read zero when the quantity to be measured is zero. So let's have a look at this systematic error, which we call a zero error. Now, if you look at this clock over here, you will notice that before the clock starts, the needle is not pointing at zero. It should be pointing at zero, but it's not pointing at zero. The needle is just after zero, which means any reading that I take with this clock is going to have a systematic error already, a zero error in it. The value that I'm going to get is going to be slightly more than the value that I should have because of the zero error already inside the clock. So this is what we mean by a zero error. Let's go back to the slide. Multiplier or scale factor error, in which the instrument consistently reads changes in the quantity to be measured greater or less than the actual changes. These errors occur with non-linear instruments when the calibration of the instrument is not known correctly. So remember, with systematic errors, we can either have a zero error or, as we said, a scale factor error, and both of these are due to the instruments themselves. Example using the dart game for systematic error. Throw one dart, throw 5 darts. All are in one spot, but you will notice that they are all above the point that we want them to be in. So let's go up to the board and have a look at a typical systematic error. So in a systematic error, the values that we're going to get are, if they're caused by a zero error, always going to be above or below. Now in the case of the clock is slightly before zero, which means all my readings are going to be slightly higher than I should get. So I get a set of values that look something like this. Yes, they are consistent, but they are certainly not accurate because they're all slightly above the value that I should be getting. So this is what we mean by a systematic error. The values are all slightly above or below the actual value I should get. Parallax error is due to the incorrect positioning of the eye. To reduce parallax error, measurement must be at eye level. So a parallax error is due to the wrong positioning of the eye. Now, a simple example of a parallax error would be using a stopwatch. If I'm going to use a stopwatch, I need to make sure that my eye is directly above the stopwatch so that I take accurate readings. If I was to put the stopwatch over here and take a reading, my reading would be inaccurate because there would be some parallax effect. I would see the needle in a slightly wrong position due to the curvature of the glass. So this is what we mean by parallax error, and it can be easily fixed by positioning your eye correctly. Parallax error in a meter reading. Parallax can be a problem when you are reading a meter. Since the pointer is slightly above the scale to allow the pointer to move freely, you must look straight at the pointer to have a correct meter reading. In other words, you must be in line with the pointer and the scale. To overcome this, view the pointer and the image on the mirror below. So here we have an example. If you look at this ammeter, you will notice that this is the needle, and below it we have a shiny mirror. The idea is this: when you take a reading, make sure your eye is right above the pointer, and the pointer and the image are in a line. If you can see both the pointer and the image, it means you have a parallax error. If the pointer and the image are in one line together, it means you are viewing the meter correctly and there should be no parallax error. Question: where will be the correct position to take the reading of the volume of the liquid in the measuring cylinder? So here we have a measuring cylinder with some water in it. Now, where would I position my eye so that I get the correct reading for the level of the water? Once again, we're looking at a problem of parallax. Now, if I stand here and take the reading like this, I would say that the reading would be 81. But if I put my head down here and I take the reading from here, I would say that the reading was 80. Now, there's a big difference between 81 and 80, especially when you're doing some type of chemical reaction, or you're measuring out an exact volume that you need for an Archimedes experiment. So this is where the parallax comes in. Now, where was the correct position? From here or from level with the meniscus? Have you made a choice? Let's have a look at the answer. The answer is C. Next question. Draw dots to represent throw of darts. Show the throws that are consistent but not accurate. So we want consistent but not accurate. So when we go back here, try and remember what consistent and accurate mean. Consistent means reproducible results, so they're all close to each other. Accurate means results that are close to the actual or wanted value. In this case, the dot in the middle. So, how would you draw consistent but not accurate? So what I need you to do is draw a circle out and using your pen, mark in the dots for consistent but not accurate. Put at least 5 dots in your diagram. Have you done it? Let's check the answer. So, as you can see in the slide, we've got 4 dots that are all close to each other, consistent, but they're not close to the center, meaning they are not accurate. Question 3. Which measurement are more accurate? So here we're looking at sensitivity. Remember, the smallest the scale division, the more accurate or more sensitive your instrument is. Now, we wrote up the ruler, the vernier caliper, and the micrometer earlier. Of these 3, which was the most sensitive? Meaning which would give me the most accurate value that I was looking for? Have you made a choice? Good. Let's check the answer. The answer is C, using a micrometer. Summary. Measure physical quantities using appropriate instruments. Remember, the smaller the scale, the more sensitive and accurate the instrument is going to be. Use appropriate techniques to reduce errors. Define consistency, accuracy and sensitivity of a measuring instrument. Compare and contrast consistency, accuracy and sensitivity of a measuring instrument. Parallax error. Remember, ways to overcome parallax error are by placing the eye in the correct position. With an ammeter, place it so that the needle and the image are in a line. With a measuring cylinder or any liquid to be measured, make sure your eye is level with the meniscus. That's all the time we have on this lesson on measurement. Thank you for watching ITTV.